Okay, question 4a. Calculate the binding energy of the isotope hydrogen-2, also known as deuterium. Given this information below, it's fairly easy to do. We need to first calculate the mass defect, or the difference in the daughter nucleus compared to its constituent proton and neutron in this case. So delta M equals 2.0141102 units, atomic mass units, that is. Take away the sum of the mass of the proton and the mass of the neutron. 1.007276 and 1.008665 atomic mass units. And so we get a difference, or mass defect, of negative 0.001839 units. Now, the negative sign can be ignored when you're working out the binding energy. It just simply tells us that, as we expected, that the mass of the proton and neutron, when they are separate, is actually higher than the mass when they are combined into a nucleus. So, to work out that, we need to convert this into kilograms. So we multiply by the value that one atomic mass unit is in kilograms, which is 1.66 times 10 to the negative 27 kgs. So that number multiplied by that gives us 3, just ignoring the negative sign, 3.05274 times 10 to the negative 30 kgs. And now I'm running out of room, so I will continue on the next page. So then we take the binding energy as equal to that mass deficit or defect times c squared. It has to be in kilograms, that's why we did all that work before. So multiplying by c squared, we get 2.74 times 10 to the minus 13 joules. Where c squared, of course, is the usual 3 times 10 to the power of 8. Just being careful not to forget to square that number though. Question 5, the nuclear equation for the fission of uranium-235 is shown below. You can see that this single neutron will be impacted and therefore cause it to fission, which means basically split up into daughter nuclei, in this case barium and krypton. And then, of course, a certain number of neutrons will be emitted as well. In this case, it's called K, the number we're trying to find for part A. So how to find that? Well, you just simply have to do a bit of accounting in terms of the nucleon number. It must be conserved, so on this side we have 235 plus 1, 236, and on this side we have 141 plus 92 plus K. So if we solve for K, it turns out, in this case, that for part A, K equals 3. So 3 neutrons are carried away after the fission process. B, the change of mass delta M. Now we just simply have to take these figures here, the mass of the uranium nucleus plus a single neutron on the left hand side, and we have to take away the addition of the barium mass, the krypton mass, and 3 more of these neutrons on the right hand side. So if we subtract that away, right hand side from left hand side, you end up finding the value to be 0.18601 units, atomic mass units. Now, if you did it the wrong way around, of course, you might get a negative sign. It doesn't matter, you just have to ignore that negative sign again. But you should expect that the uranium nucleus, together with its neutron, has slightly more mass than this right-hand side combination. And the difference, of course, is released as energy, which we're going to calculate as the part C in this case, once we get there. It might be useful to convert this change of mass to kilograms first of all, so we'll do that. Again, just using this atomic mass unit conversion to kilograms. So this is the same as, I'll put underneath, same as 3.088, taking a few figures, times 10 to the negative 28 kgs. So that's the difference in mass between the left and right hand side. Now, to find out what that is in terms of energy released or energy produced, we can multiply by c squared using delta E equals delta mc squared. So doing that for part C gives us the energy released, we'll just call it E, delta E I suppose is better. Delta E equals 2.78 times 10 to the negative 11 joules. So just to remind you how to get that number, you simply use this equation here. So delta M we just calculated as 3.088 by 10 to the negative 28. Just remember to square the speed of light, 3 to the power of 8 squared, and you'll get this answer here.